This week we will be dealing with optimization, and as you would know from your experience in school as well as in college, almost all optimization involves you to find out derivatives. So, in this video we will be looking at derivatives. So, of a little bit of warning, both this video and the next one, which will deal with what is called matrix calculus, will be mildly advanced material. Some of it you will once again be already familiar with in the one dimensional context or in the context of scalars, and we will be looking at the context of vectors also. We have only a few slides to go through both in this video as well as in the next, but the material is a little bit dense. So, please concentrate on this material, and if it is not very clear, you will still get clarified as the course goes on. Okay. So, let us first look at the idea of derivatives, which is essential for any sort of optimization. So, derivatives typically measure how one quantity changes when there is a small change in another. So, if you have something like dy dx, it means how much does y change given that x changes by a certain amount. Okay. So, as you would know, geometrically in a simple scalar case, we look at this as the slope of a tangent. Okay. So, if this is the curve y equal to f of x, then if this is the point, let us say P, if you differentiate y with respect to x at x equal to P, you will get the slope of this tangent. Of course, you can denote this as dy dx at x equal to P, or you can denote this as f prime, some people will simply call it P, or people will call it f prime x equal to P. So, there are multiple ways of denoting this. You would be familiar with all of this once again from your prior experience. So, we know that this slope essentially can be written as limit of a small perturbation on x. Okay, so, x plus h minus f of x by h, this of course is the limit of the secants, okay, as they go towards this point and become a tangent. So, the slope at this point x and x plus h. So, you find out the difference in values, and as this limit tends to 0, the slope will tend to a finite value, and that is what we call the derivative or the slope at that point. Now, when you have higher dimensions, by higher dimensions I simply mean you still have a scalar function, but x now is a vector. Okay. So, in that case x vector could be something like, let us say x1, x2, x3, or the figure that I will show shortly could be x vector is x1, x2, which means x belongs to R2. This is the case where x belongs to R3. Okay. So, in such a case we can have partial derivatives. So, let us look at such an example. Let us say z is f of x and y. Now, if you want to denote or visualize z, you simply have the variables x and y, as they change z changes, and you see here one whole surface, okay, for z. Now, I could want to know what is del z del x, okay, that is at a particular point, let us say this point. I might want to know if I just change x and I keep y fixed. You would have seen some such things in thermodynamics perhaps, but if you change x you change x and keep y fixed, you might want to know how much does z change. Now, the way to see that geometrically is to, let us say you draw a cross section, something of this sort. Okay. Let us say y fixed at y equal to, in this case, 1, and you can try and find out what this derivative is. A generalization of this idea is with n variables. Okay. So, here f is a function that takes in a vector, in this case the vector is a, which is in R n, which has n components, and it gives back a single scalar. And if you want to find out del f del x I, that is just like in this case I wanted the derivative with respect to x, then all you do is you change only that variable. So, in this case for example, I change only the ith variable I perturb it by a little bit. So, I do a I goes to a I plus h and then find out how much does the function change when I just change this variable, and that limit as h tend to 0 is what is called the partial derivative of f with respect to the variable x I. Okay. Now, reduced to a one dimensional problem, this is what it would look like. This is simply the cross section of this function at y equal to 1, and if I want the slope now, then all I will do is, let us say I will change x by a little bit. So, suppose I want del z del x at x equal to 1 y equal to 1, then I take a cross section where y is fixed at 1 and evaluate the slope at x equal to 1 by just changing x, and that slope will actually give me the variable the value of this partial derivative. Okay, so, this is the idea of partial derivative. Again, you should be familiar with this from multivariable calculus before. Now, we can generalize this idea, okay, of derivative to what is called a gradient, which we will be using very often. Okay, once again. So, let us say you have, let us call this x y and f of x y, you can call it z is equal to f of x y. Okay, so, you have a curve of this sort. Okay. There are several noticeable things here. So, suppose I want to say how much does the value of the function change at this point, that notion by itself does not become intelligent unless you say how much does it change with x. So, you have del f del x and you also have del f del y. Okay. In fact, instead of just looking at these two directions, so del f del x would be the change in the direction x and del f del y would be the change in direction y, you could ask a third direction, I could call it del f del v, where v is some arbitrary direction. Okay. So, if this is x, this is y, v could be some third direction, sorry, v could be some third direction altogether. So, the gradient is defined as basically a concatenation or a putting together of all these partial derivatives. So, in this case, in the two dimensional case, we have two such partial derivatives. In the n dimensional case, you will have n such partial derivatives and you would basically write the gradient of f, in my case would be del f del x 1 del f del x 2. Okay. So, in the n dimensional case, it is del f del x 1 del f del x 2 so on and so forth up till del f del x n, and I have put a transpose there to show that this is a vector. Some people eliminate the transpose, some people put the transpose, either is fine. In this case, now notice this is a vector, and we will look at a more general case of this in the next video, which would be the matrix calculus video, but this gradient is used very often. Okay. Now, what does the gradient physically represent? Okay. So, if we see that, here are a couple of figures to clarify this idea. So, let us look at the first figure. The first figure is just showing a shading. Now, imagine this curve here, if it is collapsed, okay, imagine it is a bunch of springs and you just collapse it and you will see these things here, the projection here are called contours. What does a contour mean? If I take this contour and raise it up to the curve, it is all the values at this value of x and y, all of these places z had the same value. Okay. So, these are what are called level sets or contours, which we will look at a little bit later in this video series also. Now, this is shaded according to value. For example, here the value of the function is high, here the value of the function is low. So, the place where the value of the function is high is shaded as dark black and later on it is shaded white. Okay. Now, the gradient, notice, is a vector and the direction of the gradient tells you in which direction is the change the sharpest. Okay. So, the change is the highest in the direction of the gradient. Okay. So, in this case, for example, all the change is the sharpest in the horizontal direction. Okay. This of course is color coded now. Okay. Red means high, blue means low. So, this is just simply color coded, but it is the same idea. Some of you who have worked in fluid mechanics might have seen this or even in other fields. So, now you notice this, these are arrows here and the arrows are aligned along the direction of maximum change. Now, if you have a more complex curve, something of this sort, once again you can draw the gradient field. Why is it the gradient field? At any point I have an f, I have del f del x 1 and I have del f del x 2. These two put together define a vector, and that vector is what is drawn here. Longer arrows mean higher gradient and shorter arrows mean lower gradient. Now, one useful way of utilizing the gradient vector is, as I told you before, you might not only want del f del x and del f del y, you might also want del f del v, where v is some other direction. So, suppose x and y are orthogonal and v is a third direction. Suppose you want del f del v. What does that mean? Physically it means if I move in the direction v or v hat, how much will the function change? And this is fairly easy. All you do is take the gradient which we have defined before. This is del f del x 1, del f del x 2, so on and so forth up till del f del x n, this vector dotted with the direction v. Okay. You can simply see special cases. If v was I cap, okay, or the x 1 direction, then gradient in the direction v should be del f del x 1, which is correct. Okay. So, this retains the meaning of the partial derivative. Similarly, if you take the direction 2, you will get del f del x 2, so on and so forth. So, for the coordinate axis this kind of reduces trivially, but in the general case you simply take a dot product along that direction. So, next we come to the idea of a Hessian. This is basically the gradient of the gradient. So, now remember, we will see this once again in the next slide. The gradient is a vector. Now, you are trying to find out how much does this vector change, okay, as you move in space. Now, why would we use some such complicated quantity? Because it is the equivalent of the second derivative in scalar calculus. So, all the uses that we had for second derivative, like finding out whether something is a maximum or a minimum, all those uses also pass on to the Hessian, as we will see in some of the videos in this week. Okay. So, suppose f is a function. Remember what this means. F is taking in, it is a box that takes in a vector as input. So, x is a vector and what it gives out is a scalar. In such a case, the Hessian is defined as del square f del x I del x j. Okay. So, Hessian is a matrix. Every entry of the matrix is basically a partial derivative. F is a scalar. So, the first entry is, for example, del square f del x 1 square. So, the n comma 2 entry is del square f del x n del x 2, so on and so forth. This is a n cross n matrix. You can also notice that this is a symmetric matrix. Notice that these two derivatives are the same. Del square f del x 1 del x 2 is the same as del x 2 del x 1. So, Hessian is a symmetric matrix, and from our linear algebra we would know that for real f, this means Hessian has real eigenvalues, okay, and eigenvectors. So, we will use this property a little bit later. So, one other quantity that we would like to define is that of a Jacobian. The Jacobian is the equivalent of the gradient for vector valued functions. So, the gradient, remember when we had defined gradient, simple gradient was from scalar to vector, but this assumed that the value of the function itself is a scalar. Now, you can define a more general case where you have a vector input and a vector output. A Hessian that we just looked at is very similar. you can see this as the Jacobian of a gradient. So, the Hessian took in gradient of f and gave out del square f, where f is now a vector, sorry, f is a scalar, but grad f is now a vector. In general, we define the Jacobian as del square f of x I by del x j. Remember that since f is now a vector, it is going to have a ith component. So, in general, you are going to have Jacobian, which is going to be m cross n. If it takes in a vector, the size of the vector is n cross 1 and it gives out a vector which is m cross 1. Okay. So, you can write the whole of Jacobian as a simple matrix. Okay. So, we will be using the Jacobian only very rarely, but some general expressions we will show in the next video. So, the final idea for this video is that of a Taylor series. The Taylor series is extremely useful whenever you try to approximate functions. So, this is very widely used in science. It is one of the most commonly used ideas in science. Practically anything that people use mathematics and calculus for, somewhere or the other Taylor series will pop up. Okay. So, this is true even of course of machine learning and optimization. Okay. So, there are of course many subtle things about this Taylor series. We are not going to look at that, we are just going to look at this single slide for Taylor series, and then we will be using it a little bit later, both in optimization as well as in other parts of machine learning. Okay. So, remember that when you have a scalar function, one dimensional function, that the kind that we used in school, for example f of x equal to e to the power x sin x or something of that sort, okay, you can write the Taylor series as f of x is f at some other point x 0. Okay. So, you want to approximate the value at some value x, given that you know the value at x naught, you also know derivatives at x naught, etc. So, this is the basic idea of Taylor series. Okay. So, if you have f of x, it is equal to f of x naught plus x minus x naught times df dx. This df dx is calculated at x equal to x 0 plus half of x minus x naught square d square f dx square. This is also calculated at x 0. An example of this which you might or might not have realized is our idea of s equal to ut plus half at square. Okay. So, that is very similar to this. You know, df dx is like u and d square f dx square is like a. This is the time that has elapsed, this is t square. So, the half is very similar to that. S is the total distance travelled. Okay. So, that is a special case of the Taylor series, and you can easily explain it in the Taylor series if you have more than the acceleration. So, if only u and a exist, then S's expression would be what I told you, but if you have u, a and what is called the jerk, which is the third derivative of this distance with respect to time, then you would have that plus 1 by 6 x minus x naught cube d cube f dx cube, so on and so forth. So, the Taylor series should be familiar to you, but most probably you would have not seen it in the case of vectors. Okay. So, in case x instead of being a scalar is now a vector, you can now write the Taylor series. Notice the similarity between these two expressions. F of x, now remember x is a vector, is f of x naught, which is the same thing, plus now notice this is a vector, okay, x minus x naught transpose times g, g is the gradient. Okay. So, that is for compactness I have written this as g. Okay. So, instead of df dx, now you have a full gradient, this is a full vector, this effectively is the dot product between one vector and the other. Okay. This, remember, is something that we had discussed earlier, this is called a quadratic form. So, you have x minus x transpose h x minus x naught, it still in the scalar case will be equivalent to x minus x naught square, okay. But in the vector case you cannot write it as x minus x naught square, it is x minus x naught transpose h, h is the Hessian which we had seen earlier multiplied by x minus x naught plus higher order terms. Luckily practically nowhere, especially in the vector case, do people use this. Okay, so this is usually the maximum that we will go. So we will go to the first order term which is the gradient and the second order term which is the Hessian, and this is sufficient for most practical purposes. Okay. So as I had said earlier, we had defined G as the gradient and H is the Hessian, also calculated at x naught. So this is just some preliminaries for multivariable calculus. We will be using all these ideas only sparingly, but you do need it in terms of building your intuition. So in case it is not clear, please revisit this video a few times. In the next video, we will be looking at a few simple mathematical relations in matrix calculus, okay, like this one, that is slightly advanced material.